For this lesson, we're going to introduce this concept of trigonometric identities and sort of what an identity is. Basically, an identity is when you have two things that maybe look really different, but they're actually the exact same thing pretty much everywhere. So it's not quite the same as an equation, but they tend to look like equations. So we're going to start with what are called the elementary identities. We've already introduced the 6 trig ratios. We have the primary ones, sine, cos, and tan, and then the secondary ones, cosecant, secant, and cotan. And the idea with these elementary identities is basically everything can be rewritten in sine and cosine. So for tan, for example, we have that tan is opposite over adjacent, and we've probably already kind of talked about this, but if we have a look at sine over cosine, so if I do sine theta over cos theta, so I've already got those ratios there. Sine is opposite over hypotenuse, and cos is adjacent over hypotenuse. And so if we cross out, the hypotenuse is on the bottom, they basically cancel. You could clean it up by doing a bunch of division, but they do just cancel. And what we're left with here is actually opposite over adjacent, which is our tan function. So that's going to be one of these identities. So tan theta is sine theta over cos theta. So in other words, what that means is we can rewrite tan using sine and cos. And now cotan, if you have a look at this, you can see that cotan is just 1 over tan. Right, it's the reciprocal of the ratios in the tan theta. So this is 1 over tan theta, which is just the flip of the sine over cos. So we could also just write that as cos theta over sine theta. And then similarly for the cosecant and secant, you can see that those are just the flips of sine and cosine. So again, we should have already sort of talked about this when we introduced these 3 secondary functions, but these are the elementary identities. And mostly we'll be focusing on just rewriting everything sine and cosine. So cosecant and secant theta. Okay, so a lot of the tasks that you'll be asked to do in these upcoming chapter or sections are going to be proving identity. So again, an identity, what we have here is an identity. So cotan x times secant x times sine x equals 1. So when we say prove the identity, it's not the same thing as asking you to solve the equation. If I asked you to solve the equation, usually you're finding like a finite number of x's that make a statement true. But when you're told that something's an identity, it basically means that it's always true. So it should be true for all x's. Now, I kind of want to say almost always, because if x isn't defined on one side of the equation, that's okay. But basically, it's almost everywhere true. So maybe all but like a couple of values. So we're not solving the equations. What we're actually going to do is use identities, use like small or mini identities, established ones, to verify that the left side and the right side are actually equal. So what we need to do is show left side equals right side. And so there's basically a couple steps we want to do from this. To show that two things are true, we need to work with them separately. So the first step is going to be separate the left side from the right side. That's really important because the way it reads right now, it actually says that it's true. So if I keep working with this, I'm saying it's already true. Well, why would I have to show that it's true if I'm already claiming that it's true? So what we do is we break it apart. So I got my left side and my right side, they're different. And then what I'm going to do now after that is I'm going to use those established identities to make both sides look the same. And those will be, for right now, just the identities listed at the top. There's not really much we can do with the right-hand side. It's equal to 1. So like I can't really simplify it any further. So what I'll do is work with the left side, which is a little bit more complicated. And then hopefully by plugging in those equations, usually my strategy is just rewrite everything sine and cosine. Hopefully we'll start to see the cancellations and just simplifications, and it reduces down to equals 1. So that's going to be what I do here, just everything in sine and cosine. So cotan x, so I could replace it with 1 over tan, but I'm going to jump right into cos over sine. So since my angle is x instead of theta, I'll just be consistent with that. I don't know why I started with an s there. So it should be cos x over sine x. Secant is 1 over cos x. And sine x, which is already in sine and cos. So now the only expressions I have in my equation are sines and coses. And then hopefully you can see here that there's a bunch of things simplifying. So this sine on the bottom will cancel with that multiplication of sine. And the 2 coses, one on the top and one on the bottom, will cancel. Everything cancels, so we're just left with 1. And so we're done. And usually in math, if we're finished a proof, we can put like a little box at the end. Yeah, it just kind of symbolizes that you're done, because it's not like an equation, or it's not like a formula where you plug something out and spit out a number and you're done, or an equation where you solve for x and you're done. You're done when you've like established a point, you've proven 2 things, so it's not as obvious when you're finished. So you just kind of want to point it out. So that's one example. We'll do another. Okay, so for this one, it says solve for x, cos x plus 2 secant x equals 3. So now notice the wording, the way that this question's asked. It says solve for x. So this is not proving an identity. We're not going to split up the left side and right side. This means that what we're working with is an equation. So we just mostly are going to use traditional algebra and traditional techniques to solve this. Now there's a little bit of a snag. What we can see here is that we've got cos and secant. So we have 2 different functions in this equation. So I'm not really going to be able to isolate for one of them. And I'm going to fix this by rewriting secant in terms of cos or sine. Now secant can be rewritten just in terms of cos, so that's kind of nice. So we're going to rewrite it as 1 over cos x equals 3. And now what we have is actually an equation with just cosines. It's still kind of an ugly equation, so solving it is a little bit tricky. What I would probably recognize here is that I have division by a cos, which I don't really want. So I'm going to eliminate this division by cos by multiplying both sides by cos x. All right, nobody likes rational functions, so we just make it not rational. So I'll do that on the left side. So remember, it's got to get distributed to both terms on the left and the right. So on the left, that's going to be cos squared x. And then on the second term, the coses will just cancel. So I'll just have plus 2. And then 3, and then that has to get multiplied by cos x. And so I'll just bring it over here and bring it all to one side, so it kind of looks like a polynomial. And so what we can see here is, yeah, we have sort of a polynomial, a quadratic equation of cos x. And so we should be able to solve this using our traditional techniques. If I want to do a swap for a simpler variable, I could do y is cos x to get y squared minus 3y plus 2 is 0. And that will tell me how it factors. So y minus 1, y minus 2 is 0. And so that's going to give me cos x minus 1, cos x minus 2 is 0. So cos x equals 1. or cos x equals 2. Now, hopefully you remember that 2 is not in the range of cos. Cos x cannot be 2, because cos x is always between -1 and 1, so that's not possible. But cos x equals 1 is possible. I don't really like doing the xy plane to solve cos x equals 1. So I like to actually do the graph of cos. And I know it starts at the top and goes down, something like that. It doesn't look very symmetric, but that's okay. So we do get a solution right here at 1. And then hopefully you remember we get 1 actually like at every period we get that maximum value. So that's going to be my list of solutions here. So the first one is at x equals 0. The next one, the period's 2 pi. So that'll be the next one. And then another 2 pi. So x is 4 pi, 6 pi. And we can just package those all together by saying multiples of 2 pi, or 0 plus 2k pi. But that should solve the equation. All right, so those are sort of the two different things that we can do right now with these identities. And this will be kind of the theme along the way. Typically, you'll be asked to do one of two tasks, either proving an identity. So you pull it apart and simplify both sides till they look the same, or solving for an equation where maybe to get it in a form where we can use older or more familiar algebra techniques, we have to throw an identity to change things around a little bit.